It may be hard to believe, but the universe and all the matter within it is very lucky to be here. Within our universe, there's both matter, what we all see and interact with on a daily basis, and antimatter, the counterpart to matter. The only way that we know of to create or destroy matter is to also create an equal amount of antimatter. So when we look at our universe, the amount of matter and antimatter should be the same. However, practically all of what remains in our universe today is matter, not antimatter, which is not a bad thing. Because when matter and antimatter come into contact with each other, they annihilate into light. This means that if there were symmetry between matter and antimatter in our universe, it would all annihilate and there would be nothing but space and light. But how is there more matter than antimatter? We will be covering the mystery surrounding the asymmetry between antimatter and matter in the universe.
Our first theory that could explain the mystery behind the asymmetry of the universe is baryogenesis. And the theory of baryogenesis states that this process that creates an asymmetry has to do with baryonic matter. And baryons are just heavy subatomic particles that are made up of 3 quarks. And this process is hypothesized to have taken place in the early stages of the universe. So, in the beginning, right after the Big Bang, the universe was so hot that no baryonic matter could survive, and there was mostly radiation. And as the universe expanded, it started to cool down, and there was a short period of time when the created matter and antimatter could survive. During this production, quarks and antiquarks and photons were in thermal equilibrium and had equal numbers. And once the universe cooled down to a certain point, quarks and antiquarks and photons were no longer being made, and there was a set number of them. And since the universe we see today is mostly made up of matter, then we can suppose that some interaction of particles caused a small difference in the number of quarks to antiquarks. And this difference can be made if certain conditions are met. Let's say that in our universe there were 800 million antiquarks for every 800 million and 3 quarks. Then the pairs would annihilate each other and create photons, leaving 3 quarks and 1.6 billion photons behind. And this is the resulting baryon to photon ratio that we see today in our universe. The creation of a matter-antimatter asymmetry seen in baryogenesis is theoretically possible where none existed initially if certain conditions are met. And these conditions are called the Sakharov conditions, found by physicist Andrei Sakharov.
These conditions are baryon number violation, C-symmetry and CP symmetry violation, and also interactions out of thermal equilibrium.
And the first condition is this means that the number of particles and antiparticles being created is not equal to the number of particles and antiparticles being destroyed. And this condition was already met in the beginning of the universe when the universe cooled down below the energy threshold needed to create particles and antiparticles.
Since CP violations play a very important role in explaining the dominance of matter over antimatter in the present universe. So what is CP? CP stands for charge and parity. Charge symmetry or conjugation symmetry means that the laws of physics are the same for particles and antiparticles. For example, if we replace a proton instead of an electron, the laws will still be the same. The only difference will be noticed is the sign difference. But essentially, we're gonna have the same result and the same outcome. And parity symmetry is just a measure of the symmetry of a physical system. In physics, a system is said to have parity if it is unchanged under transformation that inverts its spatial coordinates. An example will be a mirror. A person with the left hand will see his reversed left hand in the mirror. And this in physics means that the laws should still be the same.
And the final condition is that there must be an interaction that violates the conservation of the baryon number. In particle physics, Quarks, antiquarks are given certain values, and the conservation of the baryon number is violated if the sum of the baryon numbers of particles before an interaction does not equal the sum of the baryon number of the result of the reaction. And we will later explore some of the experiments that help verify if these conditions can be met.
Another very prominent theory about how matter edged antimatter is that of leptogenesis. Leptogenesis suggests that the antimatter asymmetry is a result of neutrinos and antineutrinos in the universe. So what are neutrinos? These are minuscule, massless particles that travel through space. They fall under the subatomic particle category of leptons. Several particles, some you may have heard of already, fall under this category. Some other leptons are electrons, muons, tauons, etc. One special quality of neutrinos is that they are their own antiparticle, in the sense that at some points, a neutrino can be an antiparticle, while at others, it is a particle. As shown on the left, some atomic particles can either be leptons or hadrons. Leptogenesis is an extremely complicated theory in particle physics, but we'll try to give a brief overview. The theory originates right after the Big Bang. The universe was so hot at that point that the laws of physics we know today did not apply, and almost everything was massless. This theory is based on 4 beliefs. There existed an undiscovered particle known as the right-handed neutrino. This particle had a very large mass, even in the conditions of the universe back then. Secondly, a particle can be a neutrino and antineutrino at the same time. Thirdly, there was neutrino CP violation. And finally, back in this early stage of the universe, there was a process known as the Sphaleron process that converts leptons to baryons. Revisiting the first belief, the physics surrounding the mass of the right-handed neutrino is assumed to be unknown. This is because it does not get its mass in the same way that all other particles we know do, the Higgs field. For the second belief, the term for that is Majorana, when a particle is its own antiparticle. For the third belief, there is C and CP violation because for some reason, the right-handed neutrino decays more often into an antiparticle than a particle. The last theory is the most complicated because it only applies to the state of the universe at this early stage. As stated earlier, it is a process that converts antimatter leptons into matter baryons. As mentioned as well in earlier portions of this episode, there are baryons and leptons. Baryons each have a baryon number of 1, and leptons have a lepton number of 1. But for antiparticles, these numbers would be negative. In our current universe's physics, baryon number and lepton number are conserved, because whenever there is a reaction between particles. However, back in these times of very hot conditions, the Sphaleron process only conserved baryon number minus lepton number. This means that a particle with a lepton number of -2 can turn into a particle with a baryon number of 2. This is how the Sphaleron process changes antimatter to matter. So using these 4 theories, we can say that there were right-handed neutrinos back then. There was CP violation, so the neutrinos were more often in the antimatter state than matter. When they decayed, they would decay into a special particle known as the Higgs boson and a lepton. The right-handed neutrinos that were antimatter at the same time of decay would produce antiparticles. So the antileptons would undergo the Sphaleron process that would convert them into matter baryons. After some time, the universe cooled, and the laws of physics that we know today began to apply. Due to the fact that there were more antineutrinos than neutrinos, due to the Sphaleron process, there ended up being more baryons than antibaryons, and that's what created the surplus of matter. Leptogenesis has not been proven, but there are some experiments that are currently trying to do so.
Moving on from these theories, We know that there are many different processes that physicists are investigating that could explain this missing antimatter in the universe. Any small difference between antimatter and matter could help to explain the origins of asymmetry. This has led to different types of experiments being done that contribute to our current understanding. Some involve the neutrino as previously mentioned, and others involve other particles. The alpha experiment at CERN measured the properties of antihydrogen versus hydrogen, but didn't discover any differences from hydrogen that were not expected. The hydrogen atom and antihydrogen are key points of the alpha experiment and its research. Another experiment is the Large Hadron Collider Beauty experiment, and it found that when a lambda B baryon decayed, its products flew off in a slightly different angle than the antimatter associated with this particle. This difference between the particle and the antiparticle helps further to explain why there is asymmetry. Finally, Fermilab is planning to build an 800-mile underground particle accelerator from Illinois to South Dakota called the Deep Underground Neutrino Experiment. They will beam neutrinos and their antimatter over a long distance, and if neutrinos behave differently from antineutrinos, it could be another reason why there is more matter than antimatter in the universe. Moving on to another experiment, the Large Hadron Collider Beauty Charged B Meson experiment is another important experiment that revealed CP asymmetry, which helps to confirm differences between matter and antimatter. This experiment studied the CP asymmetry in the decay of certain mesons. During this process, the effects of CP violation, or the antisymmetry between particle and antiparticle, are enhanced because there is a different chance for the particle to decay versus the chance for the antiparticle to decay. Additionally, an unexpected particle was formed during the decay, which led to even more CP violation and more confirmation of differences between matter and antimatter, and the theory of baryogenesis as CP violation is a condition for the theory. This graph, as complex as it looks, displays the antiparticle on the left and the particle on the right. There's a clear difference between the heights of the peaks on the graphs, which display the asymmetry between the particles. The antiparticle curve has a much higher peak than the particle curve seen on the right. One final experiment that displays asymmetry between particles and antiparticles involves physicists of the T2K collaboration. Here we can see the physicists inside of the large water tank that will be involved in the experiment. Their study involves neutrinos like many other experiments involving asymmetry. In the study, neutrinos are fired from a beam towards a large water tank, as we saw the physicists in, called the Super Kamiokande detector. When the neutrinos hit the water, they sometimes break into an electron and a muon. The physicists have noticed that more muons have been formed over time than electrons, and have noticed a difference between the neutrino mode of the beam and the antineutrino mode of the beam, showing another difference between particles and antiparticles, which helps to explain why the current matter-antimatter asymmetry exists. It's clear to see that neutrinos are a key contributor to matter-antimatter asymmetry. So what are the next steps? Well, let's go back to the original goal of this whole thing. We want to be able to prove why there is more matter than antimatter in our universe. But how are we going to do this? Well, in order to prove one of the current theories that we have spoken about regarding why there is so much more matter than antimatter in our universe, physicists will need to look for more violating interactions. This can either come in the form of CP violations or baryon number violating interactions. There currently aren't enough CP violations found to prove the theories of baryogenesis and leptogenesis. Additionally, looking for more baryon number violating interactions would help to explain the universe. However, this could require new physics to be discovered. Is it possible that this could happen in the near future? Only time will tell, but finding these things could help to cement our understandings of the origins of the universe and how asymmetry between matter and antimatter came about within our universe.